And now, ladies and gentlemen, please welcome to the stage, Marcia Loggins.
Good evening, everyone. I'm Marcia Loggins, Vice President at the Churchill Club, and welcome. Tonight is a special occasion as we welcome Jeff Hawkins, a Silicon Valley icon who is here tonight as co-founder of Numenta, in conversation with Michael Chui. Michael Chui is with McKinsey Global Institute. We wish to thank Citrix Systems for hosting this program tonight in their beautiful conference center. We also want to thank Numenta for making this program possible. Thank you very much. We have a wonderful set of programs for you before the end of the year, all supporting Churchill Club's mission to encourage innovation and economic growth. Next week, on December 4th, we present The New Industrial Revolution, How Will the Future Be Made? A conversation between Chris Anderson, CEO of 3D Robotics, and Carl Bass, CEO of Autodesk. Next, on December 13th, the popular annual Gadgets program is back with Walt Mossberg, Kara Swisher, Greg Harper, and celebrity geek guest Aaron Levy, who will all bring with them their favorite gadgets for this very fun show and tell. To cap off the year, on December 18th, we present The Future of Publishing with Guy Kawasaki, popular thriller author Barry Eisler, Kepler Books founder Clark Kepler, and Barrett Kohler CEO and publisher Steve Piersanti. We hope you'll join us for some or all of these programs. If you're tweeting tonight, please use hashtag Churchill Club. You'll find other Twitter codes in your printed program. And my last announcement. If you're considering joining or renewing your Churchill Club membership, now is a great time to do so. Attendees of tonight's program may join for just $99, which is a savings of $26. Please visit the registration table to find how you can sign up or for more specials available to you. Let me now introduce our interviewer, Michael Chui, who will then introduce our guest of honor. Dr. Chui is a principal and senior fellow of the McKinsey Global Institute, which is the economic and business research arm, or think tank, of McKinsey & Company. Recently, Michael was elected as a McKinsey partner. He travels the world conducting and presenting research on major disruptive technology trends, from social technologies to the Internet of Things to the subject at hand today. Please give your warmest welcome to Michael Chui.
Thank you, Marcia. Thank you to all of you. Thanks to the Churchill Club and for Citrix. So Jeff really needs no introduction. I think many of you know of his many accomplishments in his otherwise undistinguished professional career. Invented the PalmPilot, invented the first commercially successful smartphone, and now is simply using his own theory of how the brain works to analyze big data. So not much to talk about here, but we're going to spend a little bit talking about brains. We'll talk a little bit about business. We'll talk a little bit about big data. We'll have an opportunity for people here in the room to ask some questions, and then we'll finish with a lightning round of a few questions just to cap off the evening. So why don't we get started? Jeff, thanks for coming.
It's great to be here, and thanks for all of you coming out tonight.
Terrific. So the fount of accurate knowledge, Wikipedia, says you came from an inventive family. What does that mean, and what does that have to do with a floating stage?
Well, I had perhaps an unusual background or upbringing compared to nowadays, but my father was sort of a consummate inventor, and you could call him an entrepreneur. I wouldn't say he was very successful in his endeavors, but they were very varied and interesting. So he invented all kinds of crazy stuff. When I was in third grade, he was on the cover of Weekly Reader talking to dolphins with something called a Sceptron. And then he built this big round floating boat, which was the largest air cushion craft in the world at the time. And we turned it into a stage, and we toured with an orchestra, and nearly sank things. We stopped the trains out of Manhattan one summer when we ran into a bridge. And, lots of unusual experiences for a young kid.
You think that affected you?
Yeah,
at
it
all?
did. You know, in our house, the garage had more space and was better heated than the house. So we actually spent a lot of time, I'm not joking about that. So we spent all our time in the garage building stuff. And so one thing that helped was I learned a lot about tools and about materials and about, you know, handcrafting things. And that actually played an important role in my time at Palm and Handspring.
Can you say more about that? How, you know, what did that background?
I'll give you one example. Remember the Palm 5, which is a very successful product that was glued together. And we spent all this time designing this product, and down at the last moment, the manufacturing team decided they didn't trust the glue, and they wanted to redesign the product to use screws. And they just didn't want to go out with the idea that the glue might fail if someone left this product on their dashboard or something like that. So this is going to be a multi-month delay, and it was going to make the product ugly, and the whole point of this product was to be beautiful. And so I had to come in and basically say, you know, I know enough about glues, this is going to work. And, you know, I don't think how many people can do that, but I did know a lot about glues.
Yeah.
And, you know.
That's impressive.
We had drums of, you know, methylethyl ketone in our basement, and, you know, two-part glues and polyester resins and things like that, you know. So I knew something about that.
It started young.
Yeah.
So, you know, what did you study in college?
Electrical engineering by randomness.
Randomness.
Yeah, I didn't really know what I was doing. I said, oh, I'll be an engineer.
So when you graduated, you read some article which changed your life. Can you?
Yeah,
say
there
about
was.
that?
It was just, I started my career at Intel. I'd been working there for 3 months, and then I read the September '79 issue of Scientific American, which was about the brain. And every September issue is a dedicated topic, and this was about the brain. And a lot of neuroscientists remember this issue. It was very, very influential. And so there was a whole bunch of articles by famous people now who talked about the neuron and the diseases of the brain and the development of the brain. And Francis Crick, who was the co-discoverer of the DNA molecule, who I got to know later in his life before he died, he wrote the last story in that article, and it was called, I think it was called Thinking About Thinking. And he basically said, you know what, all this details in here was really interesting, and you can read all about this stuff, but don't be fooled. We have no idea how the brain works whatsoever. And, you know, he said it in a gentleman British sort of way, like I think he said, what is conspicuously lacking is a broad framework of ideas in which to interpret these results. It made an influence on me. I remember this. And I said, holy crap, look at this. We have this brain. This is the most important thing to being human is your brain. Everything we've ever done in society and humanity is a brain. And we don't have any idea how it works, yet we have all this data. So I said, that is a problem we can solve in my lifetime. And I said, that's what I'm going to work on. And right then and there, I said, that's it. I'm going to do this. I'm going to work on this. I'm at least going to try in my lifetime. And it's a long, long journey, but I've never forgotten that. And now I've been able to do it full time for over 10 years now.
That's great. At the time, so what did you do when you wanted to start studying the brain? You're working at Intel?
Yeah, I was working at Intel. I wrote to Gordon Moore. And I said, Gordon, I want to work on brains. I think Intel ought to do this because someday you're going to build silicon that does this stuff. And it didn't work too well. And then I tried to
Gordon didn't say, yeah,
no,
let's do that?
Oh, well, actually, I met with a bunch of people, and I met with a guy named Ted Hoff, who was one of the co-discoverers of the microprocessor, and he didn't think it was possible to ever understand how brains work. So then I'm not saying they made a wrong choice, but anyway, that didn't work out. And then I tried to become a graduate student at MIT, and they said, in the AI lab, and they said, we don't care about brains, we don't need to study brains in order to build artificial intelligence, and I disagreed with them about that. So that didn't work out. And eventually I got to be a graduate student at Berkeley, and then I was into that. I wrote a thesis proposal about what I wanted to do for my graduate work, and it was very well received by the Department of Graduate Program in Neuroscience. But they said, you can't do this, unfortunately, because it said there's no place you can study the theoretical underpinnings of the neocortex because you can't get funded and there's nobody else doing this, although it's a great idea. And so I said, holy moly, this is, so they agree this is an important thing. They like my ideas. Everyone agrees this is an important problem to work on, understanding how the neocortex works, and yet they can't do it. And so I said, I'm up against an institutional problem, not just a scientific problem. And so I said, what am I going to do? And so I said, I'll go back to work for 4 years, mature, learn how to make institutional change, make a little bit of a name for myself, earn a salary again so I can afford to be a student again. And I said, I'll do that for 4 years. And that's, you know, good or bad, it turned out to starting Palm and then Handspring. It took a lot longer to get out of that. because I really got wrapped up in the mobile computing space for a while.
Did you earn a salary at that time?
I did earn a salary at that time.
That's good.
But you know, it's funny, I have one of the most interesting founding documents for an entrepreneur, because the founding VCs of Palm, which were Sutter Ventures and Merrill Pickard Anderson and Ryer, I told them I didn't really want to be doing mobile computing. I really wanted to be working on brains, but the mobile computing thing was really cool. I wanted to work on that for a while, and they were concerned about it. So I had in the founding documents, basically the documents which for the funding of the company, it's listed that I really want to work on brains, and I can work on them again in 4 years. And I thought it was kind of fun, so I've saved that. But you know, we got wrapped up in the mobile computing space. It became really interesting, and it was very difficult to extract myself from that. But I was able to do that a little bit over 10 years ago, and then I got back into full-time in the brains and started the Redwood Neuroscience Institute at the encouragement of some neuroscience friends. We did that for several years, and then we started Numenta, and so we've been doing this full-time now I was doing it part-time throughout the entire Palm Handspring thing, but now it's been full-time.
There was actually a connection between, you know, the things that you wanted to study about the brains and the things you did with pen-based computing. Is that right?
There was a little bit of a connection. There was a little bit of connection when I was a graduate student at Berkeley, and there was the neural network craze was happening at that time. And so I said, oh, great, people want to understand how the brain works, neural networks. And then I got really disappointed. I got almost angry, because neural networks have absolutely nothing to do with brains, most of them, the neural network technology.
So why is that?
Because they call it neural networks, but the artificial neurons they use in the classic artificial neural networks are nothing like biological neurons, nothing. They're very superficial, and that the way they treat them and think about them has nothing to do with neural structure. It's very, very distant from what real brains are like. And no one was really taking the brain seriously. They weren't looking at the architecture of the brain. You know, the brain tells you the architecture for an intelligent machine. It's there, and you got to study it. And they weren't doing that. And so I didn't think they were going to be successful. And anyway, so there was a company called Nestor who was at some neural network conference, and they were trying to sell their neural network handwriting recognition software for $1 million. I said, well, that's a lot of money for something I don't think is going to work very well. So I said, I bet you I can do that using the math I was studying at the time as a graduate student. I said, I think I can do something like handwriting recognition. So I went home that night, and a day later I had my first handwriting recognition software, which became the basis of the graffiti in the PalmPilot. And I said, well, that's an idea. Look, we can build a tablet computer. And so basically, the first thing I did when I went back to work, I built the grid pad. Then I started Palm, and then we did the PalmPilot and all that kind of stuff. So there was a connection there, but it's a marginal connection.
Yeah. How have things changed in being an entrepreneur over the years? You know, you've been around the Valley for a while and started a number of companies.
Yeah, it changed in terms of what the environment for entrepreneurism, funding. What are you thinking about?
All of them.
All of them. I don't know if it's changed much at all. I mean, this is a great place here. I used to live in Boston, and that was another high-tech center, but there's no comparison. Silicon Valley is really a great place to. You could be a successful entrepreneur here and not even have to work too hard. I mean, well, I had this rule that I was going to have breakfast and dinner with my children every day, and that I wasn't going to come in the office on weekends. I'm not saying that works for everybody, but that's what I did. And you know what? And you can do that here if you partner with people who work hard. I say that.
Should we tell Donna that?
Yeah, no, but look, I mean, you can do this. There's such great infrastructure here. There's great funding here. There's great access to people and technology and intelligence and networking and so on. So this is a great place to do this. And so that's always been the case. I don't know if it's changed a lot over the years. You know, what we're doing now at Numenta, which is really, in some ways, it's a remarkable thing. We did some very deep fundamental science before we built the product. And in the past and even now, you can't get funded to do that. I could have never, Numenta couldn't have been VC funded from the start because there was no product concept. There was basically a research agenda, and we had to do that, and so we had to fund it internally. But I don't think that's changed. I think that's the same way. I don't think there's been a lot of changes in the basic structure of how you start companies here. Some of the biggest changes that I've seen are the ability to do things on a lower budget. You know, the access to all the free software and tools and software development tools is really quite different. We build our product on the Amazon cloud, so that's very low capital cost for building products. So those things have changed a lot. But I think the fundamentals of starting businesses, I haven't really seen that big a difference.
What about funding? You mentioned VCs. You mentioned the fact that Numenta is primarily privately funded.
But that was just because of the nature of what we're doing. A lot of the venture capitalists, they lament the fact that very few companies are trying to do something really unique in deep science. Another image posting website or something. But the funny thing is that often they can't fund that stuff. It doesn't fit into the model of venture funding. I mean, venture funding is they have a portfolio of companies. They have certain those individual fund goes for some number of years, maybe 7 years. They have certain horizons in which they want to exit by. And if you just come in and say, hey, I'm going to do some research and figure out something pretty cool, and when I do that, I'll figure out what the business is, and then I'll hire the right team, and that doesn't sell very well. But that's okay.
How will that stuff get funded then?
Well, I don't know. I can just tell you what I did, but I don't know what other people would do.
And what did you do?
Going back to my time at Berkeley, when I was confronted with this, I said, boy, I have an institutional problem. I can't do this as a graduate student. I can't do it as a business person. So I have to figure out the wherewithal on my own to do what I want to do. And I put into place a very long-term plan. It was a very long-term plan. These are the things I'm going to have to do. I'm going to have to accomplish them by this ages in my life. And part of that was getting into a position where I could afford to do the research that I wanted to do and fund it if I had to. So that was a conscious effort. My time at Palm and Handspring, I joke about this, but it's partially true. It was kind of like the actor waiting tables when they're trying to get the acting gig, right? I was, okay, I'll start Palm and I'll do that because I need a job. And but I got really into the mobile computing space and it was exciting. But really, that's not what I really wanted to do long term. It was something else, and so that was a means to an end.
Yeah. Did that plan work out? Was that
so far?
Was that the plan?
I'm not done yet, but yeah, it's worked out pretty well. The only hard part was really extracting myself from the mobile computing space because we had a lot of success, and there was a lot more to be done, and I basically just had to leave. I said I'm going to run out of time in my life if I don't get back into the neuroscience. And so it was difficult to do that. It's difficult to extract yourself from companies where people may have come there to work for you and you're a key player, and it's just hard to do that.
So for people who have a plan to create two world-beating, incredible products, right? I mean, one might be a coincidence, two is a bit of a trend. Any advice for people who want to create a consumer hit?
Yeah, sure. I don't know if I call it consumer hits, but I think there's a general trend advice I give to most entrepreneurs, especially if you want to do something that's difficult and challenging. Because there's some companies you can build to say, okay, I'm going to spin this and sell it in 2 years. A quick spin on something. But if you're trying to do something that's really hard and you're a bit ahead of the curve, which for some reason I seem to be attracted to, then you have to be very, very passionate about it. You have to care deeply about that thing you're trying to do, because all hell breaks loose along the way. All kinds of crap hits the fan. You're going to be challenge after challenge after challenge, and how you get yourself up over and over again to say, okay, I got to go solve that problem. I got to go solve that problem. How do I overcome this challenge? You've got to be passionate about it. Palm almost went out of business because of the early failures of our first products and other people's products. And why did we stick it out? Well, we stuck it out because we believed passionately that the future of personal computing was going to be mobile computing. And we just had to stick with it, and through thick and thin, all kinds of problems. The company was sold multiple times. Very difficult. But if that passion is there and you care deeply about the end result, you'll do what has to be done. And the same thing with my work in neuroscience. It's very challenging, very difficult problems to solve, lots of institutional weirdness to deal with, and you just got to keep getting up and saying, why am I doing this? My wife used to say, you don't have to do this. Why are you putting up with this? And because sometimes I'd come home and say, oh God, let me tell you what happened today. And so, and the answer would always be the same thing: was, well, I care deeply about what I'm trying to accomplish, and I have to do this. I have to, do crazy things sometimes to bring about the end result that we want, even if it takes years. So I think that's a good lesson for all entrepreneurs, is just, be passionate. You've got to be passionate about your work. Otherwise, you're not going to grind it through.
Speaking of crazy things and being an entrepreneur, notably, despite being a co-founder multiple times, you're not the CEO generally. What's behind that?
Well, I think we ought to recognize what we're good at and what we're not good at, and we ought to try to bring our skills. This is a common mistake I see a lot of entrepreneurs do, especially the entrepreneurs tend to be the early people tend to be the technologists, the scientists, the visionary type of people, and they often make this mistake of thinking that they don't want to give up control, and that's a fallacy. What you want to do is you want to have success. In some ways, getting more people involved, committed to your idea is the way to be successful. Getting more people worried about the success of your company is a good idea. That's investors. You want your investors to have a lot of skin in the game because you want them to sweat it out too. Like, oh crap, I can't lose that investment. Better work harder at this. And having a CEO who's really good at certain things and that complement your own skills is a great way of going. So for many years I worked with Donna Dubinsky at Palm and Handspring. Now I work with Rami Braniski right here, who's our CEO at Numenta, and we bring complementary skills to the party. He brings the operational and the sales and the marketing aspects of things, and I can bring more to the technology and sort of longer term vision of certain types of things. And that's a great way to go. It's great, and it's great to have a partner you can basically cry on their shoulder with sometimes.
How do you instill that same passion that you have in the other people that you bring on?
Well, it's pretty obvious when you're passionate about something, and if you're trying to do something really big, there's other people who want to do that. I mean, you have a PhD in cognitive science. Why did you do that? I think you did that probably because at one time you said, boy, brains are pretty cool, right?
That's true.
And, and so like in the brain science stuff, there's a lot of people who are interested in that. The work we're doing with data, there's a lot of people interested in data. And if you come in and you say, look, I've got an idea here, I believe in this, here's a different approach, and people say, yeah, I think that's right. And every day you come to the office and you try to motivate people. And you say, you know what, we're doing this, it's important. And you've got to believe it, it's got to be honest, right? You can't be dishonest about it. So I can't lie about it. So it either comes through or it doesn't. And if you pick things you're passionate about, then it comes through, and then people generally want to follow you to some extent.
Yeah, you've talked about these big problems. Peter Thiel has famously said we wanted flying cars, and instead we got 140 characters.
Yeah, what do you think about that? Was a very clever statement, and there's some truth to it, but there's other things that aren't true to it. We also got DNA sequences that you can do for $1,000 for a human genome. We've got the internet. We've got a lot of things besides 140 characters. I think what he was lamenting, and I think a lot of investors do this, as I mentioned earlier. They lament they wish there were more fundamental advances going on, and in the beginning era of Silicon Valley, people were inventing chips and analog processors and this and this and this and this and this, and it seemed like there was a lot of fundamental innovation. But the fact that we talked about earlier, that the barriers to starting companies is lower now, you get a lot more sort of, maybe less fundamental startups. And I know there's a lot of VCs who kind of lament that, and they say, boy, we wish we had more people trying to do big ideas and big things. And I imagine that's what Peter said about that. But it's true, but it's also not true. There are some really cool things that people are doing out there, and just maybe the ratio has moved a bit. There's a lot more of simpler, 140 character type of things out there.
What do you see that's cool that's going on out on that?
Well, I'm pretty myopic or focused. I think about brains. I don't try to think about too many other things. I think about data. But I do think there's some other cool things that are happening. The whole field of outside of my area of expertise, really, what's going on. I mentioned the DNA sequencing, but basically learning to control the biological processes inside of cells is very cool. And I'm sure there's going to be just amazing breakthroughs that come out of that. That's an area that's very, very exciting for me. Really, I mean, we're talking, 100-year, 1,000-year type of things where, points in the human evolution where major things happen.
Yeah.
Right. Of course, I believe that the work we're doing, both on the neuroscience side and the data side, are like that. They're fundamental things. I think they're really important to work on. I'm passionate about them, and but I don't consider myself a futurist, or I don't consider myself a technologist. Like, I look broadly at all kinds of stuff. I'm pretty narrowly focused in my world and what I do.
I'm curious about one thing. You know, some people have said there's a renaissance in hardware, right? And you've spent time with a lot of glue and screws and all that kind of stuff. You know, there's a maker movement. There, vertically integrated models, et cetera. Is there something to that in the Valley now? Is that something that?
I don't think anything's really changed. It's funny. When we started Palm, my VC backers, I said, look, I want to build these handheld computers. And the VC backers said, no, you don't want to build computers. Nobody builds computers and makes money at it. You know, you need to be a software company. And I said, really? Okay. So we'll be a software company. That means we have to partner with someone to build the hardware. Well, that was a disaster. Our first product was partnered with Casio and Sharp, and it was a total disaster. And in the end, I said, no, we got to build the hardware too. That's the only way to build it. You got to build the hardware and the software together, do an integrated solution. That's the way of doing it. And that was running counter to the ideas. And when I remember we went back and told our backers that we were going to build hardware, they almost fell out of their chairs. They said, you got to be joking. This is the death knell. They're like, writing us off on their balance sheets. And I said, but that's the only way of doing it. And now it's really popular again. Like, oh yeah, Apple's shown you can do the integrated software hardware thing. Well, okay. That's always been there, and there's always people doing clever, chip stuff, and you can look at all I can give numerous examples. So I think there's this idea that there's these trends, like only, but I don't think it's really true. People are doing both. We have people wanting to do hardware versions of our algorithms at Numenta, and so I think that's really cool, because it gives a whole new. I gave a speech in July at the International Symposium on Computing Architecture, and I'm giving one in 2 weeks at the International something. Well, these are computer scientists, and the one in 2 weeks, I'm sorry, I can't remember right now. It's a consortium of the computer consortiums. It's essentially all the.
They're very upset at you right now.
Yeah, I know. Don't listen to this. It's got another hard to remember acronym, ITRA or something like that. Anyway, I can look it up on my phone if you want. But I think there's going to be a renaissance here. You realize that computers have been built. All computers, every single type of computer, has been built on the same basic idea since the 1940s, and it's the von Neumann architecture. It's the stored program logic and stuff. And what we've learned from brains and the stuff we're doing at Numenta now is fundamentally different. This is a memory system that's distributed, and it has some really unique attributes. One of the things that the hardware guys are excited about is it lets them break through some Moore's law limitations, which they're all worried about. They're all worried about running to the end of this stuff. That's why I've been giving talks at these conferences about computer hardware people saying, what are we going to do next? And they've read about our algorithms. They understand what Numenta's doing. It's pretty exciting, and so they want me to come speak about it. And so we got some interest going on here. But for example, our systems are inherently, they're kind of neural networks. They're modeling a layer of cells in the neocortex. And they're not kind of, they're actually exactly what they're doing. They're modeling exactly a layer of cells in the neocortex. And it turns out that these are distributed systems, distributed memory, and so there's no single point of failure. So every neuron, every cell, every dendrite, every connection could fail, up to some percentage of them. There's nothing critical. And this is the way brains are too. We lose cells, we lose synapses, whatever. And so this gives us the opportunity to start building semiconductor geometries, which are small enough that we have some percentage of failures all the time. As you can say, well, what if 2% of my memory cells in my semiconductor are faulty? Well, that's unacceptable in today's architectures, but it's totally acceptable in the ones we're building now. So there's a tremendous excitement around this that you can start. We have a new paradigm, perhaps, of using these sparse distributed memory architectures, is what we've developed at Numenta. And for building intelligent machines and memory systems that are inherently fault tolerant and therefore give new opportunities for semiconductor design parameters. Well, I'm working very closely with some people at IBM on this right now. So that's pretty exciting. So I think that's going to happen over the coming years. And the hardware, it comes and goes, but I don't think it's disappearing.
Yeah. So in the book that you wrote on intelligence, you actually talk a little bit about how chip architectures could potentially change based on your view of how the brain works. Without going through all of entire chapter 6 in the book, what's your view? What are the important things about how brains work? Yeah.
Okay. Really short. I'll try to summarize it. Number one thing is the brain is a memory system. It's not a computer. It's a memory system. You learn how to do everything. That seems pretty obvious when I say that, but for 50 years, AI has not been thinking along those lines. They've been thinking along the lines of programming things. Bill Gates said it right. He was talking to a bunch of sixth graders once. I have this quote. And someone said, Bill, is it possible to build another Microsoft? And he said, you figure out how machines can learn, and you can build 6 Microsofts. It was something like that, Bill said. And he was right. So anyway, the brain, first of all, is a memory system. And we're only mostly interested in the neocortex, which is about 75% of your brain. That's the big wrinkly thing on top. That's where all high-level intelligence is, and my speech is coming from there, and your understanding it is in the neocortex. So it's a memory system. And then you say, well, I'll give you 3 attributes of the memory system, the top 3 attributes. One is it's a hierarchical system, meaning that physically the parts of the neocortex are connected in a hierarchy, sort of like a tree-shaped hierarchy. So it's not one thing, it's a hierarchy of things, and those things are all similar. So you've got a hierarchy of memory systems, memory regions are all doing the same thing. That was in the book. The other thing is that, that each of those, the basic memory that's going on in the brain is sequence memory. It's how things go out in time. So when you talk, I'm playing back complex sequences here. Think about what my brain has to do. I'm controlling dozens of muscles that are actually activated in tens of millisecond time frames, and playing back this very complex sequence that I've memorized or I've practiced in the past. And for you to understand it, you also have memory sequence of memory. You have to, memory sequences, you have to interpret the patterns in time. Right? It's not a static thing, and even vision is a temporal problem. It's not so that's the second thing. It's all about sequence memory. And the third thing is the type of representations used in the brain are what we call sparse distributive representations. This is fundamentally different than the way we do it in computers. Sparse distributive representations are, you could think of as lots of bits, like thousands of bits, not like 8 or 16 or 64 bits, but thousands of bits at a time, of which only a few percent, 2% maybe ones, and the rest be all zeros. Weird. It has some very unusual mathematical properties. I'm not going to go into them right now, but if you want, the breakthrough we had 3 years ago at Numenta was figuring out how to build sequence memories using sparse distributed representations. That was the thing I didn't know when I wrote the book. So those are the top things. It's a memory system. It's hierarchical. It's sequences in the hierarchy, and it uses sparse distributed representations. And you can read a white paper on our website if you really want to understand it. There's some talks online I've given about this you can listen to too.
So you figured out how brains work.
No, I didn't say that. I said we figured out a key components of the neocortex.
Okay, figure out how the neocortex works. Only the most important
key components of the neocortex. There's a lot more to it. I don't want to oversell it.
Okay.
I want to be precise about this. We figured out some very important parts, but there's more to learn.
What does that have to do with big data? How
well, think about what you do as a human. You are a streaming data engine. No, I'm not joking about this. You're born, right? Your neocortex is born, but it doesn't know anything. When you're born, you actually don't. When you come out of the womb, you actually can't see anything. You haven't learned what the world is composed of yet. It's not like you wake up and you're saying, oh, there's a glass, and let me try to figure out what it is. No, you actually don't see it when you're born. And what's happening is, you think about your optic nerve, this is from your eyes, is about 1 million fibers. It's 1 million sensors. It's not one thing. Your eye is not a single sense. It's 1 million sensors. And it's streaming in data, which is changing rapidly. And your ears are doing the same thing, and your touch is the same thing. It's streaming data coming into this thing. And it has to discover the structural patterns, the patterns in the world. And that's what you do throughout your life. You are building a model of the data that's coming in from actually several million sensory data streams. Well, and from that model, you can make predictions, like what are you going to say next at the end of this sentence. You make predictions every time you touch something and hear something. So you have this model, you're testing it all the time with predictions. You can detect when things are different, anomalies, and you can also generate behavior. So those are the 3 things this model does, is it makes predictions, detects anomalies, and generates behaviors. Well, we now have a world which is becoming filled with data. And actually it's becoming filled with data because there's many, many sources of data. You wrote a great piece about the Internet of Things. And in that piece, I recommend everyone read it. In that, it's long, but it's good.
Thank you.
In there, I think at one point you said that the number of senses is the number of sensors in the world is growing at I think it was 30% rate. Think about that, compounded annual rate, 30%. Meaning, every cell phone, every car, every building, every building control system, every server on the internet is generating data on a very rapid base. And so we actually have billions of sources of data in the world. And it's going to go to trillions. I mean, unbelievable. It's going to be just amazing number of data sources. And what are we going to do with that? Well, we can't just stick it in some database someplace hoping we're going to look at it sometime in the future. We don't do that. We have to somehow figure out how to capture the value of that data in real time and act on it in real time and incorporate it into models real time, just like the brain does. So when we made this connection, it took us a little while to figure this out, that this was an obvious thing to do, but you can see there's a very analogy between what we do as humans and with our brains and what we need to do with data in the world. We need to be able to bring data in, model it, act upon it immediately, and detect anomalies in it immediately. And so that's what we've done. We've built basically a small, very small neocortex. It's about 60,000 neurons, 300 million synapses. And it's a little section of the neocortex. It's less than a mouse brain, if you will. But it's actually quite powerful. We've tested this extensively. And it has an amazing ability to find temporal and spatial structure in data streams. And so we are now applying it to machine-generated data in the world.
So what are applications?
Well, we're finding lots of applications, and the trick is sort of figuring out which ones we go after first. We're finding applications in IT and online advertising. A big one we've had a lot of traction in so far is energy.
So what happens in energy?
Well, okay, a little bit of background here because you might not know this. I didn't know this until a couple of years ago or a year and a half ago. But you all buy electricity. You just get your bill every month, right? And you pay your bill, but you don't really get a chance to debate with the utility company how much you're going to spend on your bill. Big consumers of electricity do. It's called demand response. And they basically, the utility says to you, you know what, if you actually consume this amount of energy at 4 o'clock today, no more and no less, I'll give you a better rate. Interesting, electricity, think about it. This is an interesting fact. It just dawned on me recently. Someone told it to me. I didn't figure it out. But that the electricity is the only commodity in the world that has no storage. Think about that. There's no place to store electricity. There's a few little things, but mostly it has to be generated on demand. And so the utility companies are constantly trying to match their production with demand. So if they knew better how much the demand would be, they can actually be more efficient in generating electricity. And today they only do this with very large consumers, like big factories and so on. So anyway, there's a market there called demand response where there's a pricing and there's which varies throughout the day, and there's consumption which varies dramatically throughout the day. And if you can predict the consumption, or if you can predict the pricing, you can be more efficient and save money. Well, we can do that. That's the kind of thing we can do. And so we're doing that right now. We're basically monitoring. We can measure these things every 5 minutes, and we can make predictions for what the pricing is going to be, what the load's going to be every hour for the next 24 hours, that kind of thing. And this allows customers to basically load balance and better, more efficient usage. We're seeing the same type of thing in IT applications where people have to provision servers for meeting service level agreements about the demand, and they have to keep extra servers running all the time, using energy and costing money because they have to have reserve demand there because it takes 20 minutes to bring up a server in a server farm. Well, if you could predict the demand earlier for a particular application, then you can be more efficient in bringing up and down those servers even on a 20-minute basis, and you can save energy and save cost. And we find that in many of these applications, we can provide anywhere from 5 to 20 to even 30% advantages over existing techniques that they're using today. So this is a big thing. And what's going to happen in the future, sorry I'm running on here, but today we're doing this with large consumers of this energy and large consumers of the IT infrastructure and so on. But you can see this going down to the very micro level. Why shouldn't we be doing this on, instead of big factories, you can do it for every building on a campus or every building in a city or every room. Just to give you a flavor of where this is going, we met with a potential customer recently, who one of their businesses is they lease photocopiers. And they have tens of thousands of photocopiers. Well, photocopiers use a lot of electricity. So the photocopier turns itself off at night, or turns itself off, and you go and you want to use it. You have to wait, right? You have to put it on. It goes, waiting. So what if every photocopier could predict its own activity? It says, I'm expecting there's a 60% chance I'll be used in the next 20 minutes or next 5 minutes, and I'll turn myself on and off and give you the same, basically, service level agreement with the photocopier user, if you will, right? So you get the same, but I've saved myself 30% of my electricity. You know, it's that kind of thing where it's going to go. It's the Internet of Things. Like, how do you take advantage of these millions of data streams? So today, we're just getting started in this. But I think it's really exciting. It's like, you know, understanding the world's data, not just collecting the world's data, but understanding the world's data and acting upon the world's data is a very sort of cool idea that's worth being passionate about.
And putting brains in photocopiers.
Well, it's a double whammy win there if I get to build brains to do this, right? Yeah, so, you know, I have a side effort here, right? The side effort is building intelligent machines and starting, you know, being part of the machine intelligence revolution, which is going to happen very soon. And so the fact that, you know, the Numenta can build some fundamental technology, apply it to a practical problem is pretty cool. And it helps, they both help each other, you know. And so, you know, we hope that hopefully the success of Numenta, we hope will be a successful company. We'll use that to build sort of confidence and interest and knowledge about the neuroscience. And I met a lot of people in the audience here who came because of the neuroscience aspect of my work. You know, they're familiar with that. But the data side of it is really cool too. And so it's, you know, it's like, how do you, if you want to build a future of machine intelligence, where do you start? You don't start by building, you know, robots that go around and talk to you about, you know, the weather or something like that. I don't know. You have to start someplace practical. Like our first product, first successful product at Palm, the PalmPilot was an organizer. You think about it, it was an organizer. It was like a calendar and address book. It didn't sound very sexy, but it was the right step at that time to do getting, you know, a successful product in mobile computing. And, you know, today we have, we're building, you know, our first machine intelligence application. It doesn't seem to people like a machine intelligence application. It doesn't seem like machine intelligence, but it is. It's the beginning of that.
Well, your passion is obvious, and clearly we could talk all night, but I want to make sure that folks in the room have an opportunity to ask some questions. So,
what's the process for doing that?
There are microphones that will magically appear next to questions. It's like unsupervised learning in brains.
The questions have to raise their hands, though.
Yes, they do. That's an action potential.
There we go.
Hi, can you hear me okay?
Yeah.
Okay. Thank you very much for putting on the talk. With all this study of the brains, I want to ask you a philosophical question. And what I want to know is, after you've studied everything and you're decoding all sorts of the different parts of the brain, are you a determinist?
Am I a determinist? Well, why don't you define determinist so I don't make an assumption I know what you mean by that. I think I know what you mean with it, but I want to make sure that...
Do human beings have free will? In your opinion.
Okay. Well, I'll tell you this. Your brain is made of neurons, and everything that you do and everything you think and all your consciousness and all the stuff you wonder about yourself is neurons. Okay? It's the activity of neurons. There's nothing else going on in there. No magic sauce that's going to slip away someday and go someplace else. I'm afraid to say that, but it's just neurons all the way down. And now the question of free will. I saw, I think it was Hitchens who gave it. Was it Hitchens who gave a talk about free will? Does anyone remember? Was it Sam Harris or was it Christopher Hitchens?
Sam got a very popular...
Oh, Sam Harris. It was Sam Harris. You can go online and he has a talk he gave about free will. He basically concludes, and I think he did a really nice job, that unfortunately, no. We don't have free will. That doesn't mean we're deterministic. It doesn't mean you can say, oh, given these inputs, here's going to be these outputs. It's not so simple. It's not like, you know, a bunch of Legos, you turn it this way and it does that. But he does a very nice job in about an hour-long talk. And I actually haven't read his book, but I think the talk summarizes his book about this. Okay, well, I think he did a really nice job, and he understands his neuroscience well enough that it's pretty convincing for me. I know not everyone's convinced about that. I don't find this depressing at all. It doesn't bother me in the slightest to say that we really don't have free will. We are still, we can contemplate our future actions. We learn. We are a product of our environments as much as our genes, and all that's still the truth. But if you want to believe that there's something else besides the neurons in your head that make you up, I'm afraid that's not true.
Next question, and let's try to make it more grand.
I'm Sandra Peterson, and I'm not with NVIDIA anymore, but I used to be. And I have a question about programmable GPUs. So it's a technology that won some high-capacity computing awards, the fastest supercomputer a couple years ago. Is this a breakthrough, or
GPUs?
the programmable GPUs. Is this breakthrough or is this
I thought all
kind of more
GPUs
the
are. I thought
same?
all GPUs are programmable. Am I missing something? Does anyone else? I'm missing something about that? Yeah, they're all programmable. Well, look, I'm not an expert in GPUs, okay? So I mean, this is probably an ill-informed question for me. So maybe you know more about GPUs. I know a lot. I know something about GPUs, but I wouldn't consider myself an expert. You know, GPUs are a form of Van Neumann computing. It's a parallel version that have some very special attributes that take advantage of some of the nature of parallelism. For those of you who are familiar, these were originally designed for gaming and video acceleration and things like that. And they become a very mainstream computing architecture. They clearly were a breakthrough. They clearly they're very important commercially. They're being used all over the place. In fact, some of the early people working on looking at our algorithms are trying to figure out, can we use GPUs to accelerate our algorithms? So that's some of the early efforts that are going on there. I don't think they're a breakthrough in machine intelligence or anything like that. They are a really big step up in traditional computing architectures and obviously been very, very commercially valuable. And so that's all I can say about it, unless Michael wants to say something about it.
Your night.
I don't think that's, I'm not a GPU guy. No more GPU questions.
Next question.
Over here. Peter Meyer, in my area is creating markets, so I'm going to ask you a question about markets. When you were with Palm, you walked around with a little wooden block in your pocket and said there are 4 criteria for this product it has to meet. Do you have the same model, 4 criteria or something like that for Numenta?
No, I don't. The answer is I don't. And they're very different. Palm, we are building consumer products. And the psychology and the process of selling a consumer product are fundamentally very, very different than the process and psychology of selling enterprise products. Numenta we are selling to large companies. We are selling a very high-touch sale process. It's very interactive with our customers. We want to work with them closely, deep dive with them to understand their specific needs, where when you're doing consumer products, you have to hit a broad spectrum of needs in a different psychology. It's a very different thing. That's there's a lesson that doesn't, I don't think, carry over from one industry to another. But in the consumer space, it was very, very important to know what it's like to use the product personally, and before you've built one, to pretend you've built one, just so you can actually use it in your mind and discover what's good or bad about it. Here, with Numenta, it's a very, very different type of selling process, and it's much more hands-on with the customers, meeting with them, understanding deeply their pain points, what's important for their business, and in some sense, in the beginning here, custom crafting solutions for industries, because to integrate our product, by the way, which is called Grok, our product called Grok it needs to get integrated into the systems of the business. It needs to get integrated into their business processes. And that is not something you just go down to Best Buy and buy off the shelf, right? That's what happens with a handheld computer, but that's not what happens when you're selling a sort of a high-level systems thing. So there are some analogies I can make between the two different industries that I've been in the consumer product space and this, one we're doing now in Numenta, but there's some that just don't carry over.
Next question.
You got to have a microphone, Constantine. Just in this microphone.
Sorry about that. Jeff, other than opportunity cost for what I'll call easier problems, what do you see are the barriers to computer vision, or generally, translating from temporal patterns to spatial patterns, or even to geospatial patterns, as in live?
That doesn't sound like one question to me. Can I talk about the vision thing?
Please.
Okay, so the question is, what are the barriers to computer vision? You might be surprised by my answer about this. We did a lot of work on computer vision at Numenta, and we did a lot of research on it, and we tested our algorithms on vision problems. But the interesting thing along the way, we started doing some research about what is the opportunities in the computer vision marketplace. And everyone thinks that this must be really big. Like if you could solve computer vision, it's worth a lot. Actually, we concluded the opposite. We concluded that it would be a very, very difficult space to make a good profit in, and that it wasn't worth pursuing. And you probably don't want to hear me tell you this, because I know what you do. But computer vision. But But
Why is that?
you know what? It was counterintuitive. It's a complex story, but I talked to a bunch of people that started computer vision companies, and they had all had either acquired or failed under different reasons. And it just turns out that there aren't many applications where people are willing to pay you significant sums of money to do something interesting in the computer vision space. I know it sounds weird. Maybe I just wasn't smart enough to figure it out, but it wasn't just my conclusion. They kind of said, let me tell you, sit down, Jeff, let me tell you about computer vision. And there's another reason too, is that computer vision, if you think about your brain actually, about a third of your neocortex is dedicated to vision. I mean, huge amounts. The biggest areas in the brain are primary visual regions. This takes a huge amount of memory to solve the vision problem, but I could go into technical reasons why that is. For example, the areas in your brain involved, the area dedicated to vision are probably, I'm roughly making this 20 times the area that's dedicated to language. Think about that. That would tell you, and they're all using the same algorithm. So that tells you that computer vision is 20 times harder, vision is 20 times harder than language. And you think language is hard, right? But it turns out not as bad. So, from a practical point of view, we also realized that we couldn't actually build practical systems today using the technology we're doing today with software in a commercially viable way. And so it wasn't worth pursuing. So the combination of it's difficult technically from a memory and computing time point of view, combined with it doesn't look like there's much of a market, is let's not go there. And what we've done at Numenta is we've built a very, very small part of the neocortex. You can think of it as almost like a little auditory system or something like that, where it can look at single streams of data or multiple, like 5 streams of data at once and say, okay, I can discover the patterns in that. And remember, I said earlier, vision is like 1 million streams of data. So we can do something practical today in software in real time for good values to our customer. So we're going to start there. We'll get back to computer vision someday. I don't think Numenta will get back to computer vision someday. Probably someone else will. I think we'll be very, very busy doing machine data for many years. But I think ultimately it will be solved using the techniques, similar techniques to what we've developed. But it's not commercially the right place to go right now.
Next question.
Who's got the mic? They win.
So you mentioned that you're currently simulating about 60 million neurons.
60,000 neurons.
Sorry, 60,000 neurons.
300 million synapses. 2,000 columns.
If you could scale that up using approximately your algorithms, when do you think we can have a machine intelligence based on that approach? Or in general, when do you think we'll have a machine intelligence?
Well, the question is, I assume everyone can hear the questions. Is that true? I don't need to repeat them? Is that right?
That's true.
Okay. Well, what do you mean by machine intelligence? There's a spectrum of machine intelligence. I assume what you meant by your question is something equivalent to a human, as opposed to something equivalent to a mouse or a cat or a dog. I think we have to divorce ourselves from the idea that the goal here is to build human-like machines. I'm not saying you have that goal, but there are a lot of people think that. They think, well, machine intelligence is, C-3PO or, Terminator or whatever it is. I don't know. I don't follow science fiction very well. That's not really the goal. The goal is to take the principles of brains and biological brains and apply them to problems that benefit humanity. And that's not the same as building, walking, talking robots. Now, I'm not saying you can't do that, or someone might want to do that, but that's not my goal. So I'll measure machine intelligence, by a number of metrics. I gave a talk at Berkeley about a month ago as part of an invited lectureship. And in that talk, I outlined, we gave a philosophy, but what does it mean to have machine intelligence? And it was more of a matter, are you following certain principles? It was more about the principles you're using to build intelligent machines, not about the scale itself. So it wasn't a matter of having enough neurons, but are you using the right principles? And I laid out 6 principles, including hierarchy and attention and sensory motor integration. So it's a complex set of things. Today at Numenta, we're using 3 of those principles. And so there's 3 more to go, and some of them are big, some of them are less so big. But that's how I define machine intelligence. Are you building machines that work on those principles, not the scale of the memory size itself? Now, to answer your question a little bit more directly, can we build machines that have the size of a human brain or human neocortex? And clearly we can, not with today's technology. There's a researcher at IBM who came into my office in the spring, in April, I think it was. He's a scientist at Almaden Labs. His name is Winfried Wilke. And he blew me away. He came and he says, Jeff, he's a charming German-Australian accent or something. I don't know where he's from, but he's a charming guy. I can't imitate it, but you have to imagine him coming, Jeff, I've been studying your work, and I did a little presentation about it. And he basically laid out a mapping between all the things that are going on in the device, meaning semiconductor field, internet connects between semiconductors, board-level interconnections, all this really cool technology I knew nothing about, and saying, here is how we're going to get to a human-sized model of your software. And he understood what we're doing very, very deeply. He had read our papers and very deep knowledge of what we were doing. And so he laid out a roadmap for this. And it was like, I was just blown away. Oh my gosh, this guy's incredible. And and I'm not saying he's right or wrong, but that's the kind of analysis he takes. And to get there, this is probably a 15-year, 20-year type of process. But we want to start today. And because you have this tremendous amounts of memory. I said it's 1,000,000 times bigger what we're doing today. Well, you're probably not going to do that all in software. We have to do this hardware, and we're going to put it all together somehow. So, that's the kind of thing. There's nothing fundamental that has to be done to get there. But there's a lot of difficult engineering, a lot of difficult technology has to be developed. And if that was your goal, to get to that level. But there's a different type of intelligence. What we're doing at Numenta is basically, building, we're going to try to build billions of little brains and have them working all around the world. That's a different type of machine intelligence. And then ultimately maybe connect them together.
I'm going to put 2027 into my PalmPilot to check back with you
Yeah,
on
that's
that.
right.
One last question. Where is it?
I've
Yes.
got the mic. So I'm the winner. So I'm a big fan. Cogsci guy too, frustrated, had to start companies. But and so
We should have a little badge or something that says,
or
tried to build brains. Like,
some fraternity. And I was, active lurker on the Numenta forums, and a little bit bummed when Dilip George left. So I'm wondering, and why I was bummed is because, wow, at such a nascent time, shouldn't we all be sort of working together? And so the question specifically, and I'll broaden a little bit, do you guys still keep in touch? Are you sharing? And how do you see sort of the larger community working together to solve these problems? I mean, I realize you have a commercial aspect here.
So Dilip George was a co-founder of Numenta. He was a graduate student at Stanford when I was running the Redwood Neuroscience Institute, and he was interested in, he read my book, became interested in that, and then he started working at the Redwood Neuroscience Institute in his spare time, and then based partly on some of his interest and some of his work, we started Numenta a little over 7 years ago. And for what, as the gentleman just pointed out, that he left the company about 3 years ago. So Dilip and I are on good terms. There's no acrimony there. And we don't collaborate. It turned out that we started Numenta with this idea that we needed to figure out how to do sequence memory in hierarchies. And he was in charge of the science at the time, and he was doing a very mathematical approach to this. It was less biological, it was more mathematical. And that was fine, but we did that for quite a few years and it wasn't working. It wasn't making enough progress. It was making some progress, but not enough. And then I became more involved again, and I said, let's go back and look at some more very strict neuroscience approaches here. Let's really go back to the neuroscience, which is less of a mathematical approach. It's not a mathematically derived approach. It's a more empirical approach. And we started making a lot of progress on that. And we said, well, the company's going to go in that direction. That was a big insight we had 3 years ago, which led to our product Grok today and so on in our white papers. The only reason Dilip left the company is because he told me he was uncomfortable and unable to do the work in that fashion. He's a much more mathematically oriented guy, and he needs to work that way. There are people like that. I've seen this over and over again. So it's just the direction that the company took. And we're friends, and he's working in computer vision now, and he's in a stealth mode, and he and another partner. So I think the broader question is, how do we get communities together to work on this? Is something I'm very interested in. One of the things we did at Numenta is I want Numenta to be a catalyst for the future of machine intelligence. I want to use it to generate interest. I want people to say, hey, how do they do that? That's pretty cool. How does that work? I want to learn about that. To some extent, Numenta has been successful at doing that. Not as I want to do much, much more. So going forward, you'll see more of an initiative of us as sort of how do we broaden this out to broader communities and get more people involved. Right now, we turned the company from a research company into a product company. That's our focus right now is a product company. We need to have that product success. We brought in our CEO, Rami Brzezinski, about 6 months ago. And that's our focus. But I think you'll see us bouncing back and forth on the broader mission of machine intelligence. And that's something I'm very, very interested in. And you know, it's the world is full of lots of ideas, and I think we have to prove by example. We have to say, you know what, there's different approaches here. I don't want to get on a soapbox and say, just listen to me. Here's my ideas. You should trust me. I want to do it by example, by writing, by showing, by building products that are successful, demonstrating they work. And I believe that's the right way of building communities, right way of getting people aligned. And that's what we're trying to do.
Let's finish real quick with a few lightning round questions.
What does that mean? Does that mean I have to answer really quickly?
Yes.
Oh, but you've seen I already have a problem with
Your
that.
neocortex has to work very quickly.
I hope you've noticed that that is not one of my most salient features.
Question number 1.
How many words do I get to answer with?
If you speak quickly, you get more words.
Okay, well, I'm good at that.
What's your favorite mobile device?
Oh, that's a hard question.
You
Oh
just
my
wasted
God.
words.
I can't answer too quick. I am not a gadget freak. I am not an early adopter. Believe it or not, I am not an early adopter. My favorite device right now is my Kindle Fire.
Who has been your most influential mentor?
I'd have to say Donna Dubinsky is my most influential mentor. She was the CEO of Palm and Handspring and was the founding CEO of Numenta.
What would you advise someone to study in college if they wanted to have the most chance of being successful?
In what field? Come on. Give me.
Life.
Life?
This guy asked if we had free will.
Oh. Successful in what way? In business? In technology?
Business and technology.
Here, I'll tell you what. Study something you really, really care about.
It's good. How long will Silicon Valley continue to be the world's center of innovation?
I don't see the end to it, although I'm not saying it won't end. I just don't see the end to it.
What other region is most likely to challenge Silicon Valley's leadership as a center for innovation?
I have no idea. You know, the obvious answer would be like China or Japan. But remember Japan Inc. was going to take over the world in the mid-'80s? Remember that? They didn't take over the world. They're great. We love Japan. They're great partners. We do all kinds of great things. They invent all kinds of great products. But they didn't take over the world. They didn't take over Silicon Valley. So at the moment, I don't, it's hard. It's still the place to be.
What are the most important problems people in Silicon Valley should be trying to solve other than what Numenta is doing?
Oh, man. I think what Numenta is doing is the most important problem. So I don't think about much else. Sorry, pass.
Okay. What is the most overhyped trend in technology now?
This is a dangerous question to answer because you're going to piss people off. I mean, overhyped. Well, I do see things happening, okay? And one of the things I see is happening is right now, the field of data, big data, is a bit overhyped. It's funny to say that because we're kind of in that space, but we're not really. And so I see it firsthand. There's a lot of startups that are basically building a tremendous interest in big data these days. You wrote stories about big data. So I'm not blaming you.
I'm part of the problem.
I'm not blaming you. But I think it very often what happens when you're on the verge of something really big, people get it wrong initially, and I think that's happening a bit here.
What's the most underhyped trend in technology?
Well, one thing I hope is going to happen, I alluded to this earlier, there's some really cool startups that are trying to understand how to use biological processes as sort of computational paradigms, and how do you turn the biological processes going to our cells to do amazing things. And I think that's, I'm not saying it's under-promised. There's people who know this is going on. but I think I don't think the general populace understands the significance of it.
And if you were to start a company now, other than Numenta, what would it do?
I'd start Numenta again. I mean,
Thank you.
that's okay.
Thank you, Jeff, for sharing your insights and vision with us so thoughtfully. And thank you, Michael, for leading the conversation so masterfully. As a small token, please accept the Churchill Club t-shirt as a small token of our gratitude.
Hey, that's cool. All right, I like it. Can I pretend that the bowler hat's a brain? Can I pretend that there, there we go, looks like a little bit like it.
With the t-shirts?
What does it mean on the back? I have to figure this out.
One of us, what front, one the other?
One front, one back.
Okay.
Here we go, guys. Here,
This is like draft day. We've been drafted by Churchill Club. He's number one, he's taller.
All right,
Thank you.
Thanks
Thanks,
very much,
everyone.
Michael. And I can be around for a few minutes afterwards if people want to talk further. So.
Great, appreciate it.
All right. And our team is here, Ram is here, and Joe Zarb is here, and if people want to talk business, we can talk business.
Thank you again to Citrix and Numenta. And as a special treat for tonight's audience, a free Kindle edition of Jeff's book on intelligence is his gift to you. Simply drop your business card in the bowl on your way out to receive your free copy. You've been a wonderful audience. Have a good night, and we'll see you next time.